Vaccines Explained: How vaccines train the immune system to prevent disease. Vaccines are biological tools that teach your immune system what a dangerous germ looks like before you meet it in real life. In plain English, vaccines create a safe preview of a threat so your body can respond faster, with less damage, the next time. Vaccines matter because modern life makes outbreaks easier: dense cities, fast travel, aging populations, and more people living with conditions that weaken immunity. At the same time, many pathogens evolve, supply chains break, and public trust can swing wildly, which turns a good vaccine exists into protection actually reaches people only some of the time. This Vaccines Explained guide will show how vaccines work under the hood, why numbers like efficacy and coverage can mislead, and where vaccines shine or struggle in the real world. The story turns on whether we can keep protection high enough, long enough, and widely enough to stay ahead of both microbes and mistrust. Key points. Vaccines work by training immune memory, so the body can respond faster and more effectively to a future infection. Efficacy, in trials, and effectiveness, in the real world, answer different questions, and can diverge for predictable reasons. Many vaccines prevent severe disease far better than they prevent infection, and that is still a major public health win. Not all vaccines are built the same. Live attenuated, inactivated subunit toxoid viral vector and mRNA approaches each have trade-offs. A vaccine dose is not just the active ingredient. Formulation, adjuvants, storage temperature, and manufacturing consistency can make or break results. Herd immunity is not a magic on-off switch. It is a shifting threshold shaped by transmissibility, vaccine performance, and how people mix. Safety is evaluated before approval and monitored after rollout using multiple surveillance systems designed to spot rare signals. The hardest part is often not invention, but delivery, cold chain, staffing, schedules, record keeping, and sustained uptake over years. What it is. A vaccine is a controlled exposure that prompts the immune system to build defenses without requiring you to suffer the full disease. The goal is preparation. Give the immune system enough information to recognize a pathogen and respond quickly if it appears later. Most vaccines do this by presenting an antigen. An antigen is a piece of a germ, or a harmless stand-in, that the immune system can learn to identify. Once trained, the immune system can produce targeted antibodies and marshal immune cells that limit spread and tissue damage. Vaccination is often described as prevention, but it is more accurate to think of it as risk reduction. Depending on the vaccine and the pathogen, vaccination might prevent infection entirely, prevent symptoms, or mainly prevent severe outcomes like hospitalization and death. What it is not: a vaccine is not a treatment for an active infection, and it is not a guarantee that you will never get sick. It is also not one thing. Different vaccine platforms trigger immunity in different ways, which is why a vaccine that is excellent for one disease might be a poor fit for another. How it works. Start with the core idea. Immunity learns by rehearsal. Your immune system is built to recognize patterns, test responses, and store what works. First, the vaccine introduces an antigen in a safe form. That can be a weakened germ, a killed germ, a purified protein, a toxin fragment, or genetic instructions that help your cells make a harmless protein target. The form matters because it affects how strongly and how broadly the immune system is alerted. Next, the innate immune system reacts. This is your fast, general alarm system. It causes local inflammation, recruits immune cells, and creates the conditions for a more precise response. This early stage is why short-term side effects like a sore arm or mild fever can happen. They are often signs the immune system has noticed the signal. Then, antigen-presenting cells show the antigen to the adaptive immune system. This is the precision layer. Helper T cells coordinate the response. B cells mature into antibody-producing factories, and other T cells can learn to identify and kill infected cells. After that, immune memory forms. Some B cells and T cells become long-lived memory cells. They stick around so that, on a future exposure, the immune system can respond faster and at a lower cost. This is the central mechanism behind why vaccines can turn a dangerous infection into a mild illness, or stop it altogether. A useful analogy, used sparingly: think of the antigen as a wanted poster, not the criminal. The immune system trains on the poster, learns the face, and can mobilize quickly if the real threat shows up. Numbers that matter. A refrigerator range of 2 degrees Celsius to 8 degrees Celsius sounds like a logistics footnote, but it is a biological boundary. Many vaccines must be kept within specific temperature bands from factory to clinic. If the temperature drifts too far, the vaccine can lose potency, which can turn vaccinated into less protected without anyone noticing at the moment of injection. Some products require frozen or ultra-cold storage. That matters because each step adds cost, equipment needs, and failure modes. If the storage requirement shifts, distribution becomes easier. If it tightens, access can shrink, especially outside major medical centers. A 97% effective figure is powerful, but it needs context. For example, the 2-dose MMR performance against measles is often summarized with simple percentages. Those numbers represent relative risk reduction under defined conditions, not a promise that 97 out of 100 exposures are blocked in every setting. The real-world outcome also depends on timing, immune status, and outbreak intensity. Herd immunity is often discussed as a single threshold, but it is derived from a simple relationship. As a pathogen becomes more transmissible, the share of immune people needed to interrupt spread rises. If a variant spreads more easily, the threshold moves upward. If vaccine performance drops against infection, the threshold can move again. Clinical trials are sized in stages because you can only learn certain things at certain scales. Early phases focus on safety and immune response in smaller groups. Larger trials are needed to estimate protection and detect common side effects. Even large trials can miss extremely rare events, which is why post-authorization monitoring exists. Adjuvants have a time dimension. Some adjuvants, like aluminum salts, have been used for decades. That long tail of use matters because it expands the evidence base across many populations and many years, which is different from the evidence you get from a short, time-limited trial. Finally, 2 doses versus 1 dose is not just a schedule detail. Many vaccines rely on priming and boosting. The first exposure teaches recognition. The later exposure strengthens, refines, and extends the response. If uptake drops after dose 1, population protection can look deceptively high on paper, while being fragile in reality. Where it works and where it breaks. Vaccines work best when the target is biologically stable, and the immune system can recognize it reliably over time. Diseases like measles illustrate the upside. When coverage is high, transmission can collapse and outbreaks become rare, even though imported cases still occur. Vaccines also perform well when the infrastructure matches the biology. That means reliable cold chain, consistent dosing schedules, clear guidance, and easy access. In those conditions, vaccine exists becomes vaccine protects, at population scale. Where vaccines break is often not a single failure, but a stack of small ones. One failure mode is pathogen evolution. If surface proteins change enough, antibodies trained on older versions can bind less effectively. That does not always erase protection, but it can shift the balance from preventing infection to mainly preventing severe disease. Another failure mode is immune variation. People differ by age, genetics, health status, medications, and prior exposures. Some will generate weaker responses, which can make personal protection lower even when population averages look strong. Then there is delivery failure. Temperature excursions, missed doses, long intervals, stockouts, and fractured record systems can all erode the real-world protection that trials suggest is possible. This is the most common disconnect between lab success and public health impact. Finally, there is trust failure. Vaccines are among the most scrutinized interventions in medicine, but scrutiny can morph into misinformation. When uptake drops below the level needed to suppress spread, outbreaks can return quickly, especially for highly contagious diseases. Analysis, scientific and engineering reality. Under the hood, vaccines are an immune training protocol. They deliver an antigen signal, shape how that signal is sensed, and rely on the body's ability to store a useful memory. For vaccine claims to hold, a few things must be true. The antigen must match the pathogen well enough to prompt relevant antibodies or T-cell responses. The immune response must be strong enough, in enough people, to shift outcomes at scale. And the product must be manufactured consistently so that one batch behaves like the next. A key way to weaken an interpretation is to confuse immune markers with real protection. Antibodies are measurable and important, but protection can also involve T cells and other mechanisms. If a headline treats a single lab measurement as the whole story, it can overstate certainty. Another common confusion is demos versus deployment. A platform that works in a tightly controlled trial can stumble when it hits refrigeration constraints, staffing shortages, missed appointments, or populations with different health profiles. The biology might be sound while the system fails. Economic and market impact. Vaccines have a unique economic shape. The upside is huge. Preventing illness can reduce hospital load, preserve productivity, and avoid long-term complications. But the revenue model can be thin compared to chronic disease drugs, because vaccines are often given a limited number of times. Adoption depends on practicalities, manufacturing capacity, vials and syringes, transport, cold storage, quality testing, and consistent procurement. A vaccine that is cheap per dose can still be expensive to deliver if it requires ultra-cold storage or multiple visits. Near-term pathways tend to focus on incremental improvements, easier storage, broader age indications, combination shots, and updates to match circulating strains. Longer-term pathways push toward faster design cycles, better correlates of protection, and vaccines that are less sensitive to pathogen evolution. Total cost of ownership shows up in places people ignore: training staff, preventing wastage, maintaining temperature monitoring equipment, and supporting data systems that track doses across years and across providers. Security, privacy, and misuse risks. The most plausible misuse risk is not a sci-fi scenario. It is confusion and manipulation. Vaccines sit at the intersection of biology, trust, and governance, which makes them targets for disinformation campaigns. If bad actors can reduce uptake, they can raise disease burden without inventing a single new pathogen. There are also supply chain risks, counterfeit products, theft, and disruptions that create local shortages. When supply is inconsistent, public confidence can degrade and inequities widen. Privacy concerns tend to appear around immunization records and verification systems. The guardrails here are not only technical, they are about governance, clear limits, transparency about data use, and oversight that matches the sensitivity of health information. Social and cultural impact. Vaccination changes the baseline of what societies consider normal risk. When vaccines work well, it can feel like the disease vanished, which ironically makes vaccination harder to sustain because the threat is less visible. In education and public understanding, vaccines are a test of scientific literacy. People must accept a probabilistic story: protection is strong but not absolute, and population effects require collective uptake. If vaccination scales well, it can empower the vulnerable. Newborns, older adults, and immunocompromised people benefit disproportionately when the people around them are protected. If it fails, those same groups pay first. Second-order impacts are political. Policies around school entry requirements, mandates in certain workplaces, and emergency authorizations can sharpen cultural divisions, even when the underlying science is stable. What most coverage misses. Most coverage treats vaccines as a single question: do they work? The more useful question is, which outcome, in which population, for how long, under what delivery conditions? A second blind spot is manufacturing as science. A vaccine is not just a formula, it is a reproducible process. Quality control, lot consistency, and storage integrity are not bureaucracy. They are part of the mechanism that turns biology into reliable protection. The third missed piece is that vaccine performance is a moving target, because the world moves. Pathogens evolve, immunity wanes, people change behavior, and health systems face shocks. A vaccine can remain scientifically sound, while its real-world impact shifts, simply because the surrounding environment changed. Why this matters. Vaccines matter most to people at the edges of resilience. Infants too young to be fully immunized, older adults with weaker immune responses, and people with chronic conditions or immune suppression. When vaccines reduce spread, they protect individuals directly and indirectly. In the short term, vaccination can stabilize health systems by reducing severe disease and preventing outbreaks from becoming hospital surges. In the longer term, it shapes the frontier of medicine, including therapeutic vaccines for cancer and tailored immune approaches that blur the line between prevention and treatment. The milestones to watch are practical triggers, not slogans. Look for improvements in storage and distribution requirements, clearer definitions of protection that predict real outcomes, and platforms that can be updated quickly without compromising manufacturing consistency. Also, watch whether uptake remains high enough in key childhood schedules to prevent the return of diseases that only seem gone because vaccination kept them that way. Real-world impact. A parent brings a toddler in for routine shots. The immediate impact is invisible. The real impact is that, months later, a daycare exposure does not turn into an ICU admission, and a pregnant family member is less likely to be caught in an outbreak wave. A hospital prepares for winter respiratory season. Vaccination does not eliminate admissions, but it can shift the mix from crisis-level respiratory failure to milder disease that clinics and home care can manage. A biotech team designs an updated antigen for a fast-changing virus. The breakthrough is not only in the sequence, but in proving that the updated product can be manufactured and delivered at scale with consistent quality. A public health department tracks rising exemption rates. A small percentage shift can change outbreak risk dramatically for highly contagious diseases, turning rare into inevitable in certain communities. Frequently asked questions. How do vaccines work? Vaccines work by exposing the immune system to an antigen so it can build immune memory. Later, if the real pathogen appears, the immune system recognizes it faster and can respond before the infection causes severe damage. This can prevent infection entirely, or it can mainly prevent severe disease. The exact outcome depends on the pathogen and the vaccine platform. What is the difference between vaccine efficacy and effectiveness? Efficacy describes how well a vaccine reduces disease risk under the controlled conditions of a clinical trial. Effectiveness describes performance in the real world, where timing, storage, health status, and exposure patterns vary. A vaccine can have excellent efficacy and slightly lower effectiveness without anything being wrong. Real-world conditions are simply messier than trials. Are vaccines safe? No medical intervention is risk-free, but vaccines are evaluated in stages before approval and monitored after rollout to detect rare events. Safety surveillance exists because rare outcomes can be too uncommon to appear even in large trials. A practical way to think about it is comparative risk. Vaccination is designed to reduce the overall risk of harm from disease, even while acknowledging that side effects can occur. Why do some vaccines need boosters? Boosters can be needed because immunity can wane over time, or because the pathogen changes. A booster can raise antibody levels, strengthen immune memory, and improve the quality of the immune response. Some vaccine platforms also require multiple doses to build a durable response in the first place, especially when the immune signal is intentionally gentle. What are adjuvants in vaccines? An adjuvant is an ingredient that helps the immune system respond more strongly to the antigen. It can make the immune signal clearer, which can allow lower antigen doses or fewer doses overall. Adjuvants are not filler. They are part of the immune instruction set. Can vaccines give you the disease they prevent? Some vaccines use live attenuated organisms, which are weakened forms designed not to cause disease in healthy people. Other common platforms use killed organisms, proteins, or genetic instructions that cannot cause the full infection. The details depend on the vaccine type, which is why guidance can differ for people with severely weakened immune systems. What is herd immunity, and is it real? Herd immunity is the population effect that occurs when enough people are immune that transmission chains struggle to sustain. It is real, but it is not a permanent shield and not a single number. It depends on how contagious the pathogen is, how well immunity blocks infection, and how people mix in real life. Changes in any of those can shift the threshold. Why do vaccinated people sometimes still get sick? Vaccination reduces risk. It does not always eliminate it. Breakthrough infections can happen because immunity wanes, the pathogen has changed, exposure intensity is high, or the immune response is weaker in some individuals. Even when infection occurs, vaccination often reduces the chance of severe outcomes, which is a central reason vaccines are used at scale. The road ahead. The future of vaccines is less about one perfect shot and more about building systems that can sustain protection as conditions change. The core problem is dynamic. Pathogens evolve, immunity fades, and delivery constraints shape who is actually protected. One scenario is faster updates and easier delivery. If we see more vaccines that remain stable at standard refrigerator temperatures and can be updated quickly, it could lead to broader access and higher sustained coverage. A second scenario is widening inequality of protection. If we see distribution systems strain, misinformation persist, or routine childhood coverage fall in pockets, It could lead to a world where outbreaks return regularly in specific communities, even while national averages look acceptable. A third scenario is a shift toward immune engineering beyond infectious disease. If we see successful therapeutic vaccines and personalized immune approaches become routine in oncology and autoimmune care, it could lead to vaccines becoming a broader category of immune programming, not only prevention. A fourth scenario is governance backlash. If we see vaccine policy become more politicized and less consistent across jurisdictions, it could lead to slower adoption, fragmented schedules, and a weaker ability to respond quickly in emergencies. What to watch next is not only the next platform, but the next proof that vaccines can be delivered reliably, updated responsibly, and trusted widely enough to convert biological potential into real protection. More insight, less noise. Subscribe and explore the full range at taylortailored.co.uk.